for systematic design in LDOs topic. So Dr. Sakshi Arora completed her PhD in electrical engineering, specializing in power management IC design at Stanford University in 2013. Prior to her doctoral studies, she worked as an analog IC designer at ST Microelectronics from 2005 to 2007. Her doctoral thesis focused on high frequency multiple output DC-DC converters for SOCs. She holds a PhD engineering degree from BITS Pilani. Following her PhD, she worked at Texas Instruments Kilby Lab in 2014. Subsequently, she served as a hardware engineer and tech lead at Apple from 2014 to 2019. Her current research focus is design automation for analog IC design and hardware IC design for better health. So, welcome, Sakshi. Thank you very much, and the floor is yours.
Thank you so much, Sanjay. I must say this is the hardest slide deck for me to prepare, and you'll know why. So thank you. I will start sharing my screen now. Okay. Okay. I hope you all see my screen. Do you? Do you all see my screen?
Yes,
So
yes, it is visible. Yes.
super, super. Thank you. So today's topic is limitations of systematic design of LDOs. I think I liked how Sanjay said that was better than how I have framed it here. Challenges is a better word than limitations, because challenges sounds like exciting and something you can overcome, but limitations looks like something that you might not. So let's change the title right now and call it Challenges of Systematic Design of LDOs. Um, I'm not sure what the audience is like, but I'm assuming it's a mix of academia and industry. Is that right? Um, I'm assuming there are
Yes,
students. Yeah, there are students and there
yes,
are professionals. So
indeed.
I've kind of created a mix in my slides, which is hard. But if you find it too easy, it's okay. If you find it too hard, please let me know. So the outline is what is systematic analog IC design? Why is systematic design important? I'll take LDO as a case study, and then we'll talk about limitations, or let's say challenges of the methodology, and potential solutions, which we are working on aggressively these days. So the first one, I thought I'll talk about what is systematic, but then I realized just 5 minutes before the talk that why is more important than what. So I've flipped it around and we'll talk of why first. So why is systematic design important? So analog IC design is known for a few things. I knew this like 20 years ago when at ST, I think it was the same. In my undergrad, it was the same. Now also it's the same. And that is these words are thrown at us like crazy, which are it is hard, it is intuition heavy, and only smart folks can do it. I don't see it as a compliment anymore because I think being on a pedestal is something that we need to celebrate, which means we have to put in more effort for more students to be able, or more people to be able to come to the field that I love, and I'm assuming most of you who are here love analog a lot. And I think isolating ourselves and somehow celebrating ourselves and being more brainy is not solving the purpose. So let's get down and then let's get more and more people. And that's why I have this talk today planned. So bottom line is it's hard to automate analog IC design. If you've been a practicing analog IC designer, you would know there's so much intuition, so many trade-offs. There's a hell lot of stuff going on, and thinking of automation of layout is at least one thing, but talking about design automation in analog is I'm not sure how many of you feel that way, but leave me a message in chat box if you feel the same thing. But it's hard to recreate design unless we have the same PDK. I cannot emphasize this more. I have students who take papers, print them out, come to me, just recreate them on Cadence, and then the results would be completely off. It's immensely uh, hard, if not impossible, to recreate the performance that papers have because of the fact that unless you have the same ditto PDK and maybe the senior designer next to your chair, very hard to recreate design, which is good and bad. I think time is gone that we call it good. So let's challenge this theory that uh, it's intuition heavy. Having said that, before I proceed, I fall in the bucket of, and I take the blame myself to derive a lot of joy in analog, just thinking and then just designing without putting pen on paper. So I think that's where the challenge is coming. So let's go a little further. Why is that a problem? Why is intuition a problem? Or why is uh, being hard a problem? The problem is lack of reproducibility. It is very crucial in today's days and age because it creates barrier to innovation. Now this is very important because uh, earlier it was, I think it was still okay, but if you come to my place where I've transitioned from industry to academia, holding students attention where there are tons of fields around which have quick results, they can have an FPGA board very quickly, showing them the performance compared to long cycle time of analog IC design. So you might think that these students are not good, but they might be good and still not choosing analog, which is not good. You know, we want the best folks to come to our field. Because of that, reproducibility is a very important thing. And I think I'm not the only one talking about it. There must be people in this presentation today who might think the same or might think exactly opposite, and that's all okay. But I am mostly inspired by Professor Boris Merman. I think all of us might know about him. And I can't forget his word. He used democratizing IC design as the key word and most important thing for today. Second is, without a standardized process, how do you expect people to innovate unless they spend lots of time, which today's generation may or may not have? I don't want to generalize, but we all know that there are so many things existing today. So this is a problem. So we have to make sure that intuition heavy things are reduced. um, I'll go into a lot of technical stuff in a minute, but motivation first. Analog design paradox. This is a paradox that I deal with every day. The first one is, I want people to become good analog designers and still celebrate intuition. This is something that is not just me. I think practicing analog designers here will resonate with me when I say that we want people to be good analog designers. We want them to celebrate intuition, but at the same time, when you are teaching people intuition, there needs to be a methodology to it. Without methodology in the initial years of their work, building intuition becomes harder. And which is why you would see that designers take a lot more time to become good analog designers compared to good digital designers. Leave it in the chat box if you think what I'm saying is making sense. At least this is what I've experienced in both industry and academia, that the barrier to entry is higher for analog compared to other fields in ECE or computer science. Um, so once we understand this analog design paradox, which most of us who have been in the field for quite some time would resonate with, then why methodology first? I think all of us agree that methodology is important, but I want to make a case that methodology is one of the most important priority for today. And why do I think so? First is open source analog IC design. I'm sure all of you know that there is lots of emphasis and money and expertise going into making everything open source. Skywater, IHP, I think GF also has open source efforts, but I'm sure most companies are getting into it. I could be wrong because now I kind of have little insights into what's going on the other side. But this is important for us to grow. The second one is ML for analog circuits. Now I can't tell you how much I hate and love this part at the same time. I'm working on machine learning for analog circuits with a professor who's an expert at machine learning at IIITB. And every time I go to his meeting, it feels like I am betraying analog to an extent. But at the same time, I think disrupting ourselves and challenging ourselves and getting out there and be like, okay, no, I love this field, but at the same time, you know, it's important to keep our minds open. So it's important to at least think of how machine learning can help us. The third one is training new engineers. This is I'm super passionate about it, making it simple for them to learn. If you want to help me, we have lots of uh, platforms where you can help. Second is saves time in the long run, even for the experienced engineers. Last one is easy to port designs in new nodes. This is so important. If we can make our designs or methodology PDK independent, think of the benefits we can have and think of the time saving that we can have. And this is not just me. If you are a student listening to me, this might be a little um, uh, not so easy to grasp, but if you're in industry, this might be a moot point. So this might be like, oh, this is obvious, right? We want to reduce the time when I'm moving from one node to the other. So methodology first. So that's the idea behind all this. Now let's get into what is systematic analog IC design. When I say what is systematic analog design, it looks like I have some recipe or something which others don't have, and which is not true. I think everything we have been doing has a system to it. Let's see what all can be a systematic analog design. And I think I have a huge respect for anyone who's doing analog IC design, regardless of the way they do it. It could be intuition. If you talk to senior senior analog IC designer, they can look at a circuit and they'd be like, yeah, you know, size this one bigger, this one smaller, this one is like. I remember my first mentor in analog was on phone told me how to design a latch. It was a latch, no, sorry, there was a level shifter. This level shifter was giving us problems. So I was going from home to office, and on phone he would say, you know, M1 को इससे connect कर, इसको इससे कर, इसका size ऊपर कर, and he had no pen and paper. He was just talking in, you know, thin air. And we've all seen analog designers like that and being awe of them. So intuition is strong. So that is also systematic. It's not that they are, you know, fluke. There's no randomness to it. They have a system, and that system came from experience. So let's respect that. The second one is spice monkeying. I know most of us look down upon it, where you can just, you know, increase W by L, reduce W by L. Is it going up? Is it going in saturation? And keep cranking numbers till you get a circuit to work. We've seen that. But that's also a system, a random system, but I would not call it a non-system. Now I've seen students very quickly doing spice monkeying and getting a circuit to work more than I would do, because there are so many tools at their disposal. So I've started to, you know, not disrespect anyone who is getting into this domain. The third one is full design automation. This is something which will not come as a surprise to you. I could automate the hell out of the circuit and be like, okay, you know, give me this performance and sweep every single thing and get the performance. Can someone, I think I can hear noise. Can someone maybe mute them? Can you please mute yourself? Yeah, thank you. The last one, which will be the emphasis for today, is LUT-based approach. I'm sure you've heard of GM&ID based methodology. I'll do a quick review for those of you who are not exposed to it. If you're interested in going deeper into it, please feel free to reach out to me. I can conduct a separate tutorial session for GM&ID based methodology and how to create circuits using that. Personally, I transitioned from first category to fourth category. At Stanford, I learned about GM&ID methodology from Professor Merman, and I'm sure now it's like common knowledge, or maybe not, I don't know. But it was so powerful because of one line, and that is first time right design. So I was used to iteratively designing analog circuit and then build intuition. But GM&ID methodology is very powerful, or LUT-based methodology is very powerful in designing analog circuits systematically. I will walk you through the process, but before that, let me compare these. And for comparison, we need to understand there must be students in the talk. And if you are taught square law at school, which is mass in saturation, ID is proportional to VOV square or overdrive voltage square. If you've been taught that, I'm sure when you go to industry or when you are starting to design your own circuits, it will fall apart and break your heart at the same time. That why were we taught this when it's not going to hold true? So what do we see here is there are three process nodes that one of my students took. It's 180 nanometer, 130 nanometer, and 45 nanometer process. And x-axis is overdrive voltage, y-axis is GM by ID, which is transconductance divided by ID. Ideally, it should just be 2 over overdrive voltage. So the red plot is what you should get if the square law that you've studied at school, or sorry, by school I mean undergrad or grad, if it were true, you would have seen some plots like this. But when you actually go simulate, and even worse, when you measure, you will not see something like that. It'll drift apart, especially when you go closer to subthreshold, or when you are, how do I say, lower overdrive voltages. So they'd start drifting apart, which means our analysis where, hey, I'll size the transistor based on square law will no more hold true. So what do? I have no structure in place. I have no square law in place. And the senior analog designers in my office can design circuits like this. So where am I? So the entry level engineers might be super confused and at loss, because analysis is one thing and design is another. If you read Razavi's book, this is what I tell my students all the time, that Razavi will make you an excellent um, a person who can analyze analog circuits. But to design analog circuits, you need to design it. You have to get your hands dirty to get your design in place. So once we've understood that Baba square law is not holding true, so again I go back to what all I have in my kitty. So what is systematic analog design? I could go for square law fitted model. Here I compare 3 ways of designing analog circuits. Trust me, if you leave it to me, I would not go through this process. I would sit with my schematic and size it. But when you are on the other side of the table, and when you are making sure that the new designers are trained, you have to step back and think of the best approach to teach them. So I could go for square law and fitted model, which means square law or some fudge factor put on square law as a function of parameters. The second one is full design automation. As I said, just automate everything, sweep everything. And I've seen students do that. So you can have that full design automation. And the third one is LUT-based approach. There are many things you can compare this to. First is analytical insights. I would not give up analytical insights for anything. If machine learning comes tomorrow, I think still we all analog designers should fight for the intuition that is years of knowledge we have. So analytical insights still there. If you have square law or fitted model, you might not get to the close, like sub 5% error, but you can still get a feel of how to design circuits, which is so important for analog. Second is full design automation. Analytical insights lost. So topological innovation is hard. So you just give FETs and then you size them, sweep them, size them, bring it back. For 5T error amplifier, it's okay, you can do it. But if you get complex circuits, done. LUT-based approach can actually do that. I'll show you now in a bit. Reduce iterations. So square law has iterations. We all have done it. If you do square law, then you are out very far from the expectation versus reality is off. Then you keep tuning, and then you get closer. Full design automation, obviously iterations would be lesser. LUT-based approach, yes. So iterations are lesser. Primarily, I'm trying to make a case for LUT-based approach, but model accuracy, obviously low for square law, because square law is not holding true, as we said. By the way, I still think square law is very important for everyone to learn before they go into any other thing in analog design. Model accuracy, FTA is good. Now, open source IC design friendly is very important. A few days ago, there were students of mine who were working on Skywater. They came up to me and they found quite a few cells in Skywater, which is open source, which they could reuse. And that time I realized that, okay, it's not just farce that open source will turn the game around. Because if I am building a complex circuit, I don't want to spend time, maybe I do, maybe I don't, to build a comparator which has been done before. I would just leverage it. This problem industry might not face because you have libraries where you can fetch it from. But if you truly want people to learn, then we have to make it accessible to everybody, which is why open source is very important, especially now that I'm in academia. I think it's very crucial, which is why LUT-based approach helps. Ease of automation, we cannot shy away from it again. So I think you can argue with me, but I will still, because this is me talking, I would still make the case for the third one. And I've seen it in action, and it's so good, the GM on ID methodology or the LUT-based approach. Now let's go into it. I've been building up, so I will give you a glimpse of it also. LUT-based approach versus the traditional way of designing. This figure is taken from Professor Merman's book. By the way, most of the inspiration is Professor Merman's. Specification, hand calculations, circuit, SPICE results. This is what we do. There is BSIM model, there's Hazard models that you go into SPICE. The problem is that there are poor approximation of square law. So your hand calculations versus your SPICE simulations will not correlate, which is a sad thing, but that can happen to you if you are designing, unless you are designing in a really, really old process node. This is the problem which you will face if you are a student or a new designer. Seasoned designers wouldn't even worry about the left part, I think. I could be wrong here. Now, for LUT-based approach, what we do is take the PDK, characterize it like crazy, characterize FETs like crazy, one-time generation, create lots of lookup tables. So in my head, I think of lookup tables replacing square law. There'll be challenges which we'll obviously see, but that's what we are doing. Instead of one equation representing a complex behavior, we are saying, hey, you know, I can't have one equation represent the whole gamut of behaviors that PMOS and NMOS can show. How about create lookup tables and characterize the FET first time I get the PDK? So I tell the students that once you get a PDK, sit with it, sit with the transistors. Do not start designing your circuit. Sit with the transistor, have your cup of tea, characterize it, use technology plots, show you how to do that. But once you have it, then start designing. So befriend your MOSFETs. If you're using MOSFETs, FinFETs, whichever blocks you are using, befriend them first and then start designing. So that's the idea of a GM on ID methodology. I'll also show you how to do it. Now let's get into deeper and deeper. So we are going breadth first, motivation first, and then we are going into how to do it. I'll just take a pause and see if I'm online, if people are still listening. Quick check. All good? People are listening to me, right?
Yes, Sakshi.
Oh,
Yes.
good.
Indeed.
Yes,
Why
all
not?
of us are listening to you.
I was just lost in my slides and being happy about presenting without thinking what's happening. Okay, so the next thing is GM on ID flow essentially uses 3 figures of merit, or let's call it 4. I'll show you why. First is the GM on ID, which is current efficiency. How much transconductance you can get for a unit of ID is called GM on ID. Square law will tell you it's 2 by VOV, but it'll drift as we just saw. So we can just say, hey, you know, proxy is a word that Boris uses. So let's use GM on ID as a proxy for 2 by VOV. So if you're making a paradigm shift from a square law based design to a GM on ID based design, these are the first few months of getting familiar with it is a good thing. So keep in mind that GM on ID is nothing but 2 over VOV. That's one. Second is intrinsic gain. Intrinsic gain is something which is not a new thing in GM on ID paradigm. I think it's there in, if you're doing square law also, you know GMRO, which is the intrinsic gain. I'm assuming the audience here is at least familiar with first few chapters of Razavi, and I've designed a few circuits. So GMRO, which is 2 by VOV. So see, there's this dependence on VOV throughout. Transit frequency, FT, again, GM by CGG, or the capacitance, that the gate capacitance that we see, FT, is again proportional to overdrive voltage. The good thing about all of them is that they are width independent. So we created new figures of merit. Another figure of merit which is not shown here is ID by W. I'll show you next. In current by width, or the current density. So this is how, once you characterize your MOSFET, the plots look like this. X-axis is GM on ID for everything. And y-axis is 3 figures of merit, which is why we call 3 forms, because x-axis is GM on ID and now y-axis are 3 figures of merit for the transistor. There is intrinsic gain, there is ID by W, and then there is FT. And we sweep it across multiple lengths. So you plot these, and so this is what Boris used to tell us, and I tell my students now, that once you are starting, plot these, put it on your desk, print them out, and then you can just, have a look at them when you are designing on the wall. So you have any new PDK, do this for all the devices that are available to you, vis-a-vis PMOS, NMOS in our example. So these forms will characterize your MOSFETs. Now say I'm done with the characterization, what do I do? So remember, we are doing a paradigm shift. So we all know square law. You can all size W by L for a square law, I assume. If not, please go. If you're a student, you can go and revise how to do it. It's just ID is beta by 2 VOV square. W by L comes there. So you can have W by L evaluated from that. Here the focus is GM on IDs. Now I have transistors which are characterized. What do I do next? I do this. I'll show you one small teeny mini example for a transistor. Suppose I ask you to calculate W by L. In the title, the slash is gone. But suppose I'm asking you to calculate the aspect ratio for a transistor. I'll give you the current. I'll give you the intrinsic gain I want. I give you the VDS. What will you do? You characterize the FET. First plot, look at the plots on the right. X-axis is GM on ID. Y-axis is intrinsic gain for the first one. And ID by W, or the current per unit width, for the second one. Okay. So let's walk through this example so that you know in the next slides what I'm going to talk about. Say I give you a certain intrinsic gain. For our case, say I give you a gain of 100. So you say, you know what, let me choose GM on ID of 10 because it's a proxy for overdrive voltage of 200 millivolt. Say you choose overdrive voltage of 200 millivolt, which might be too much for ultra low dropout regulators. We are struggling with it, so we have throttled it even further. But say I start with this, good starting point. So GM on ID of 10 on x-axis, first plot, I use 10. I go all the way up, look for what length should I choose for minimum intrinsic gain of 100. And I'm like, okay, let me choose 900 nanometer. You all with me, I hope. So the green plot gives me, should I zoom in a little bit so that you can all see? Yeah. So 10, and then I go up, and then I'm like, okay, let me choose the length of 900 nanometer. So I have my length, but I'm still left with the width. Now I come to the next plot, which is the ID by W. Now I'll give you the current. So I remember I gave you the quiescent current, or the current that goes through the FET also. So you know the current, and you also know that GM on ID is 10. Again, 10 and 900 nanometer, I come up here and I can find my ID by W from this one. Say it is, say 4 or 5, I think, I don't know, but we can go here and then look for, maybe the number is 3, 4, whatever. Now you get that ID by W number, and that's absolutely true because you characterize the device to begin with. There's no approximation we made, no square law model here. This is true device characterization. Now you come to the left, now you have to find the width. I give you the current, you divide the current by ID by W, you get the width. And you put this W by L in a MOSFET in your schematic, wherever you're running. You run the simulation, 100% match you will get. There is no way you will not get the match. I will challenge all this when I talk about challenges. For now, if I give you the VDS, if I give you the intrinsic gain I desire, if I give you the current, you will be able to size the W by L. For seasoned designers, this might be easy, but for new designers, think of this slide as your gold slide for moving from square law to GM on ID methodology. Now I could give you FT, I could give you intrinsic gain, I could give you ID by W. Whatever I give you, you go back to the tech plots and find the length. And then once you have the length, you find the width and you are done. So this is very easy, but as life is, nothing is easy. In an analog design, absolutely nothing is easy. You think everything is done, and then problems starts coming, constraints start coming, and then you're like, oh, I thought I'm having an easy dinner, but nothing like that comes. So by we have understood how to size a transistor. This is what we actually, when we are teaching GM on ID, we do this. So once you have the figure of merit for the transistor figured out, I know this is the gain I want of the FET, you are done. That's pretty much getting to the last ball of your wicket. I don't know, I'm bad at cricket, but last ball of the over बोलते हैं ना, last ball of the over, और जिसमें आपको एक रन बनाना है, maybe it's an easy breezy thing. So, but the hard part is if I give you bigger schematics. So now we are doing LDO as a case study. Now this is very important. Why LDO? Why are we using LDO as a case study? So we could use two circuits, which I think are good circuits to start anytime you are trying to demystify analog circuits for students. As you would have guessed, if you are an experienced designer, that first is a two-stage OTA, the second one I think is an LDO. And I give LDO a bigger or a higher weight to an OTA for this simple reason that when you are designing an LDO, very few, or maybe the first time you design an LDO, you can not worry about thermal noise, but there is a dynamic nature to LDO, which is the load is changing, which means the stability of the circuit will change with respect to load. So LDO is a classic case study for any time you're trying to understand the systematic design of analog circuits, because of which I've taken LDO. By no means LDO is a trivial circuit. I think I will say it slowly because I think it's important. Two-stage OTA and LDO are both basic but non-trivial circuits. Uh, if you are in industry, you will, I think, appreciate what I said. But if you are in academia or you are a student, you might think, so our students come up to me and say, hey, why do we study LDO first? Why are we not studying PLLs? Why are we not studying ADCs first? So I always tell them, कि पहले LDO बनाओ, पहले two-stage OTA बनाओ, then we'll talk. You know what I'm saying? So give me a thumbs up if you are in industry and you think this is kind of maybe true, that we need to teach them OTA, LDO first and then proceed. Okay. So I'm mindful that you could be a seasoned designer. So we will take the talk in both a high dynamic range talk I have tried to make. So let's talk about LDO performance metric. This is for students. This is not for someone who's practicing designers. So LDO is low dropout regulator, but um, the mother of it is linear regulator. And dropout voltage is nothing but V in minus V out. So what is the lowest input voltage for which the regulator would be like, oh, I'm not going to regulate anymore. That is called the dropout voltage. So low dropout is very important for one purpose, is super crucial for efficiency purposes. Think of an IoT node where you have an LDO or a load or a regulator. If your dropout voltage is huge, it's just a resistor. I mean, not a resistor. If you compute the efficiency, it's just a dissipative element. So you don't want to burn. The higher the dropout voltage, the lesser your efficiency. So we don't want to do that. So I hope you've seen this feedback circuit in your undergrad, which is you take a PASFET, you take a transistor, we call it a PASFET or a power FET, depending on where you work. Industry companies can vary their names. And then you have a PASFET. So this is just a negative feedback loop. Simplest form of understanding an LDO is ये एक output से pass FET है. There is an output voltage where the current is being drawn. There is some kind of a load cap, and then there is feedback, and then the output voltage goes back, and then you have a regulation in action. This is feedback. Line regulation is when you are changing the supply, and then how does the output voltage change? These are not transient. Line regulation is not transient. It's a steady state kind of a metric. Load regulation, same thing applied to the load. Load is changing, and then you evaluate the regulation. PSRR is power supply rejection, very crucial for the applications that we these days are interested in. RF के लिए important, IoTs के लिए important, PSRR very important. DC and the worst case we are interested in. It is how much output voltage changes when you have a noise at the input voltage. This is unlike line regulation with AC performance. So we do AC analysis if I'm trying to do PSRR. Transient, it's a simplistic thing here. There's it's a complex thing because slew is also involved. But if you're, for the topic for today, it's systematic design. So I kind of simplified this for you if you want to just quickly go over why linear regulator. So I emphasize here that two-stage LDO and OTA are basic yet non-trivial analog blocks. Okay, so let's see. Now we are going into, so we started with why systematic, then we went into GM on ID methodology. Now we are using that GM1ID methodology and designing the simplest possible, I think simplest possible LDO, which is externally compensated LDO. You have, by external compensation, I'll give one sentence for the university students, is compensation is you have multiple nodes in a circuit. You want, if all of them are having the same time constant, you have an issue, you have a problem. And the problem is that your circuit will become unstable in nature. So we want the time constants every node ka to be separated out. So we want, that's also called pole splitting if you've studied in your this thing. So split the poles, separate them out. So you have a pole at the output, which is the CL. You have the pole at the output of the error amplifier, and then you have the pole at this mirror node. This mirror node, as you would have guessed, this is not a class, so I'm not teaching, but this impedance is very low. You can go study further why it's low. It's a very simple thing. So these two are the important nodes that we're interested in, the output of the error amplifier and the output of the LDO. Simple thing. Why we study LDO for systematic design is the, as I said, dynamic nature of it, which means load is changing. So here what you're seeing on the right is there is a pole at the output, and then there is a pole at the output of the error amplifier. When you change the load current, so remember it's a regulator, so the load that it is supplying can change. It might or might not, but mostly almost all applications that you think of will have a varying load, which means when load changes, so the output pole is a function of the output impedance here, which is primarily RO8 by RO3, parallel RO3. So when you are drawing the load current, this RO is a function of load, so it will change. This is square law approximation. It would not hold like this, but the trends hold true, even if square law doesn't hold, which is why I think it's important to learn square law. So if you're drawing load, the second pole, the output pole, is going to move out when you have heavy, light load to heavy. Heavy is nothing but more load, or the higher load. Huh? So your unity gain bandwidth will also move out. But your first pole to first order, first pole as in the pole of the error amplifier to first order, will remain same. So what we think in back of the envelope calculations or the first pass analysis to determine which one is the worst case condition, we'll say, hey, load will change. If the load changes, the pole will move out, this pole will move out, which means my phase margin will actually get worse because the poles are coming close to each other. Summary of this slide is when the poles are closest to each other is your bad case. You don't want that to happen. You want them to stay far from each other. So whichever LDO you open, first things first, look at if my load is changing, is the condition getting better or is it getting worse? So in externally compensated, it gets worse. So we say, hey, let me start my algorithm. So now we are moving from a paradigm of analog design to more thinking as an analog, as a algorithm analog. So algorithms for analog kind of a thing. So which is why trends are important. So I understood this. Now, just as a homework for students is, if I have a Miller compensated of if P1 was dominant, what would you think would happen if load would change? Becomes worse, becomes better, or stays the same? That will give you an idea that one LDO is like, this is the simplest LDO, but all LDOs can be different. Okay. So first thing is know your system before crafting and using a methodology. So we have this. Now say I give you certain specs. Every time we have, for industry, it's very simple. Like we took simple specs. So you have supply, but the supply will not be constant, it will be varying. There's output voltage. It's a very simple case to see how I go from an analog designer to algorithm analog, right? Systematic. So you take certain specs. Now we are going into something which I at least didn't do as an analog designer, is looking at algorithmic approach. So first thing is size the pass FET. So you had a big transistor, we start with that. Again, we assume a certain GM1ID, you have a CL. Then what you do is, because it has to support a big current, you either use minimum length, or if minimum length is not allowed in the PDK, or you have some DFM rules, etc., then you choose a bigger length. But that thing is kind of a thumb rule that you would know from your folks. But say I have some minimum length that I can stick to. So what do? You have GM1ID of 10, which we start from. But if your dropout is lesser, you can adapt to it. Your minimum length you choose. Then we follow what we studied earlier, which was now I have GM on ID and I have L, which means I can go into finding the ID by W for the FET from the figures that we studied earlier. You saw, remember, we had characterized the FET, this one. So here we know GM on ID and we know we are designing for minimum length. So we can find ID by W. And you know, heavy load is your worst condition, which means you can find the width of the pass FET. So this is a very simple step-by-step method, but in your head, you will see that we are going step by step, which means we are going in an algorithmic fashion and shifting a little bit the way we think. And then what we do, we again look at other technology plots, and then we say, you know, GM I can evaluate because GM on ID I know and I load I know. So if you see, every equation here is banking on the technology plots and not some fudge factors, not some equations. And the merit of that is it brings system to analog design. And that system is lookup table based approach. All these equations that you are seeing here, except the equation number 5, I think all of 3 and 5, you would have seen if you're conventionally designing OTAs or LDOs. So 3 and 5 are telling you that I took tech plots, FT tech plots and ID by W tech plots, and I sized my pass FET in seconds. There is not much news here except for the fact that all this can go in a Python code. As an analog designer, I feel that, as I said, Python coding and analog circuit design sounds like sacrilege is what you say, or maybe it's like betrayal, but let's say it's very good. Once we get used to it, algorithmic approach to analog circuit design can help us tremendously. Next, now once you have pass FET ID by W, you can have, so this is just, I'm giving you an example how we look at LUT based approach to to analog IC design. So you get all the technology plots, GMRO, ID by W, FT. Here I have just one technology plot. Why? Because I know I'm designing for minimum length. So I can extract the performance and then feed those results to the differential amplifier, because those are the two blocks that I'm going to design. As I said, I took the simplest LDO because this is what what I was going to discuss today, which is LUT-based approach to designing circuits. We are using the same methodology, but developing for different LDO circuits like FBB, FVF, any LDO circuit you think of, we can develop these methodologies using tech plots. So now we are coming to the second stage, which is sizing the error amplifier. Again, this is algorithm number 2. So now you see that we are just shifting our paradigm and we're calling them algorithms. Sizing of the diffamp, we have GM pass, RO pass, which is the intrinsic gain of the pass FET, you know, the first pole because externally compensated it was, CGG pass, you know, from FT, you know, I bias. So you will go through a set of equations, which is now the only difference between the traditional way of designing and this is nothing here is left to guesswork or square law. Everything here from diffamp gain is the loop gain that you want divided by the pass FET gain, because I know the overall gain from the PSRR spec or load reg spec, anything. Unity gain bandwidth, here I think we have changed the flow a little bit, but omega P2, so second pole you can derive like, oh, I want 45-degree phase margin, I'll put the pole here, and then you can get the output impedance of the error amplifier, and then you can find, again, the GM by ID of the diff pair. Once you have the GM by ID of diff pair, same flow you follow. I want a certain intrinsic gain. I have a certain GM by ID, which I have evaluated from the quiescent current that you gave me. Same thing that I showed you earlier, that once I have GMRO, I have GM by ID, I'm done, because I'll find the length and I have the ID by W, I'll find the width. Before I proceed, oh, sorry, I wanted to show you, these are the tech plots. Now for error amplifier also, we use tech plots and then we design it. I'm not sure how many of you realized, but till here, we started with the fact that let's target methodology first approach, which is less intuition heavy. So if you realize till here, I did not make any guess. It is all very methodical, very step by step, no approximation, no fudge factors, no nothing. It is a transistor characterized and those characterized lookup tables used to design circuits. If you are using GM1ID to design circuits, this might be like 101 for you. But if you're not, then this might be a little irky for you also, like doubts might be there, which is why the presentation is today. So till here, I can confidently tell you that this works shockingly well. How? So we gave this flow to a first time designer, to a student, and they would just go step by step by step by step, and loop gain calculated is handcrafted, because when you say calculated it looks like we use square law. No, it was handcrafted is what I think both Jesper and Boris call it. So it is most using tech plots, because 60 dB, then simulated 60 dB, error 0%, pole 1 0.82%, pole 2 2.3%, unity gain bandwidth 1.16%, phase margin 0.58%. Now if you are in the initial years of your analog circuit design, these numbers might be like, oh my god, wow, they are too good to be true. If you are in later stages of analog circuit design, you'll be like, these two I can get without even using all this drama of GM1ID. And if you're a student, you might be thinking, wow, there is a methodology in place. And I think the first and the third are what we think should be targeted, because seasoned designers don't need all this for PMOS LDO. If you design PMOS LDOs, you'll be like, it's so easy, right? But the power is not PMOS LDO. The power is that it can be extended to anything. A student of mine is designing folded cascode, and then I don't know if you remember, but designing folded cascode for the first time is hard, because you will have so many transistors going into triode, wo triode mein ja raha hai, ye linear mein ja raha hai. But he could get it in the first time. And that is the power of GM1ID methodology, and lowering the entry barrier, like the first time barrier. For seasoned designers also, if you're designing complex circuits and technology porting, it is like minutes, right? And it's truly too good to be true. But like everything, there are problems. And I have limited, I know I'm tied to time. So I'll transition to limitations of methodology. But before going there, I want to do a quick review of where we started, where we are as a story. So why systematic design? Super important. We cannot evade it. Open source is coming, machine learning is important. It's better that we disrupt ourselves than someone else disrupts us. Someone who is trained in analog IC design, which is why I would request, if you've been years into analog IC design, please get in touch with me. We have a lot of work here and you can help us tremendously. So I would request seasoned analog designers to actually help us disrupt it before machine learning folks disrupt analog design, because which is not what we want. So wealth of knowledge there, right? So why is systematic design important? I think barrier to entry, machine learning, open source, reduce design time, very important. What is systematic analog design? Everything is systematic. A person who's tweaking also thinks that it is systematic. There's a systematically tweaking. But to us, systematic means first time right. Matlab, you have to have a transistor characterized the way it is, which is technology plots. Get the plots out of the FET and then start designing. And you can put a method to it, like put a flow to it. That flow which is rid of any assumptions. As circuits get complex, it is inevitable. I know it will be make assumptions. That's okay. Third is low dropout voltage regulator. As a case study, we took a simple LDO circuit. And even if in that LDO circuit, I said it's non-trivial, because across load, it is giving you good correlation, which is a good thing. So low dropout voltage regulator as a case study we saw, and we saw how to size the FET and how to size the whole LDO. Till here, I hope you are at least 50% with me. And now I'll bombard you with bad news. So good news is good news. Now let's go into bad news. Analog isn't easy, and I would say, yeah, I agree. So first, I have put limitations so that now I'll borrow Sanjay's word. Let's call it challenge. Whenever I say limitation, you read it as challenge, because we are working on overcoming them. Yeah. First is topology specific flow, which might sound intimidating to maybe engineers who have less than 5 years of experience, but more than that, I think it is not news to you. Topology specific flow is bound to happen. You cannot have an FBB LDO, FVF LDO, externally, internally compensated, capless, all those having same flow, not possible. I think it is important to realize that GM-on-ID methodology and lookup table methodology is not a one size fit all. It is only saying how to size a transistor without using square law, and how to change your flow of thinking and embedding GM-on-ID in your flow. So it is not saying I can design one algorithm for all LDOs or all OTs. No, right? Folded cascade will need its own flow. By own, I mean adapting this thing. Backbone stays the same. You have to compensate, etc., etc. So algorithm one, say capless LDO, has different. Algorithm two, externally compensated FBB LDO. So we can design an algorithm given certain specs and conditions. And this is not new. Now what I've started to do is every student who works with me, I tell them एक circuit है, and उसके साथ you should have an algorithm. And if that algorithm is switching states, etc., you should capture everything in that algorithm. So from my perspective, the big learning has been that I'm a super, like, I love analog a lot. I might not be the broker, etc., but I love it like a lot. But still, thinking of analog plus algorithm is the way to go, because it helps students grasp very well, very well, methodical thinking, and slowly they build intuition. So first is topology specific flow. The second, which is a very important challenge I wanted to share with you, is when you start designing GM-on-ID methodology, there'll be a huge hit you will see as an impact of VDS. And this is why I kept it a secret till now. How do you generate tech plots? To generate tech plots, this slide actually is created by my colleague Manikandan. So I want to give him a credit. This slide I borrowed from him. He helped us create, like, how do you generate tech plots? It's a very standard way. You take a transistor, you sweep VDS, you sweep VGS, you plot what we were saying. You plot GM-on-ID, GMRO, ID by W, FT. Sweeping VDS we put in the end, because earlier we used to think that I'll take VDS and I'll create tech plots and then I'm done. The problem is, in your real circuit, DC operating point will change. Everything will change with respect to VDS. So you need to have a priori information on approximate how much VDS. For students, I think you know what VDS is. I'm assuming you know VDS. You need a priori information on what VDS is to actually use those tech plots. Now, if you go back to my slides, I'm not sure if I'll think about whether to share it or not. I think it's okay only. You can go back and see that for every tech plot, on the top, it's written VDS of what value? VDS of 0.4, VDS of 0.6. So these technology plots are VDS sensitive, okay? So which means, one second, I think I missed a plot here. Okay, so there's a plot missing, there's a slide missing here. The slide was saying, for if I sweep VDS, the tech plots, the technology plots, which you were thinking as two-dimensional, I'm not sure if you remember, but we just saw that technology plots are 2D in nature, right? Every tech plot, let's see. Yeah. So if you look at GMRO tech plots, it's 2D in nature, right? I just GM-on-ID, GMRO, and then I have multiple lengths. I can just look at the plot and then design. Imagine now you see I've written VDS of 0.4. Now imagine I'm sweeping VDS also. So there are multiple tech plots for GMRO. So which means I have to pick which VDS to choose first, and then I will go design it. Again, it will be super precise, super crisp, but the process is a little bit more tedious than one shot or like easy breezy. It starts to get complex a little bit. Okay, so what do we do about it? This is something, it's not there as yet. I think we are working on it, and perhaps we'll think about how to publish it in this thing. It's very powerful in reducing your computation and all those things. Use subtech plots. Subtech plots is, you do a first pass analysis of your circuit and get the DC op, not the DC op, but ballpark DC op. Like, for example, for a pass fit, I would know what is my dropout voltage, min, max. So I'll generate tech plots only for the values I'm aware of. For example, in a supply voltage of, say, I'm doing a 1.2 to 0.9 conversion for an LDO, none of the transistors is going to see full 1.2 volt, right? So generating tech plots for a VDS of 1.2 is a moot point, right? So you'll not do that. So that's but making these technology plots intelligent so that they don't occupy the the whole machine is full of technology plots. We don't want to do that. It's not necessary, but I think we are doing it in anticipation that in the future this might be a big problem. So you create a sub-technology plots. Not a hard thing to grasp. Once you design it, you will understand that it's important to generate a little teeny mini subset of it. The second thing is dynamic nature of LDO. I spoke about it earlier also in context of heavy load versus light load and stability. Dynamic nature of LDO is not just coming with for stability. The problem is for supply rejection also. This alpha business here I'm showing is a factor that we have derived. It's a function of VDS mismatch. But if VDS is mismatched in the error amplifier, you can see a supply rejection varying across when you draw load. That is something that can throw you off, right? I am varying my load, VDS changes, and VDS change. Which tech plot do I look at? Now, if monotonicity is there, you are good. I know that I'll take the worst case, but if monotonicity is not there, it's hard. So we have faced it once and it was easily fixed because VDS, we got the ballpark number of VDS and we're still predicting, and worst case PSRR we hit. But I'm just leaving this open that if monotonicity is not there, if you're doing PVT, etc., if you break monotonicity, which I'm sure if you've designed circuits, you know that it can happen, then this is a problem. Then you have to think about what to do. I think we're still working on these problems. So all these problems are bonus on square law. So I hope all of you agree that we have left square law far behind. We are just doing like how to get this methodology adapted across wide range of audience. The next one is second order dependence. So crucial. This is something we've not seen in until 65 nanometer, we didn't see it. But I think 45 nanometer, we were simulating and we saw that width is also important. You remember I showed you tech plots that width, these figures of merit were independent of width. And this is something, if you go read the classic paper, you read the papers on GM&ID methodology, width is not captured at all. So you can have certain width, characterize the tech plots, and you're done. Very good methodology. It is width agnostic here. Because we did ID by W, I hope you noticed that we normalized across for width. But for lesser and lesser process nodes, I'm sure 28 and below, this can show a dependence. So this one I've put here because I'm not very confident. I don't have quantified results for it. But because the topic is on challenges, and we've started to see that there is dependence on width, we need more conclusive designs. Because of which, if any one of you is interested in partnering and trying out, and you do see, then this is like a good meaty problem to solve. To use tech plots at the same time, keep them less complex so that people can use it. Complexity badha ke to you can do anything, but we want to keep it simple at the same time design it. So you could sweep for width and you could create hazard data for width sweep, VDS sweep, but then it defeats the whole process because analog design is the charm is intuition. If you cannot see circuits and you cannot guess that how a circuit would behave, too many tech plots and very heavy tech plots will take away from that. At the same time, if you can keep your data simple, you can now, as I was saying, it's okay to start thinking about how to use automation for sizing, right? So we can feed the design. This is some work by one of my students, Anvit. So what he did was he took all the design specification to put all the LUTs into a script. So he feeds the CSV into a Python script and also the GM&ID methodology for every LDO in the script, and it spits out W by L. Now this is different from full design automation because they are very aware the script is designed by the student. He or she knows that how I size my W by Ls. So my constant challenge is to make sure that we do not go towards full design automation too much that we cannot innovate on topology, because I think that defeats the whole purpose. Unless a designer sees and faces the constraints, there's no way he or she can automate. But this solution is only for the fact that if your technology plots maybe have a certain depth, like maybe different VDS or widths, This is an open thing. And I think scripting for fetching WBILs is not new. We are just doing it for multiple VDS, etc. This I think is commonplace, and it's not hard because you just have CSV files for all the technology plots. You have a methodology or spitting out WBIL. Why we can use it? Because we have put paper pay the methodology. If I was still having intuition in my head, there's no way you can code it up. So this part, I strongly believe you have to learn to put your intuition on paper. Initially, when I was teaching, I found it really hard. Trust me, for every LDO, I would write up a code. It would be hard because I would like, अरे इसको तो ऐसे ही size कर सकते हैं. You can size it like that, no? But then you have to think hard and think hard about, oh, you can use GM&ID methodology and then size it. And once it works, it's all worth the effort. And I'm saying this with confidence that I've designed with or without GM&ID methodology. And I would strongly recommend, if you have designed LDOs, please speak with me. I want you to try GM&ID if you're not trying already. If you're trying already, please share. Please come to us and have a talk in our university. I would just like to summarize, and we are sharp on time. Sanjay, time ko I honored. Summary is, first one is, why are we doing all this business when we can design using our conventional ways? If you've not moved already, is open source analog ICs, and that's like a paramount thing. I don't think we should shy away from it. Very important. And unlike ML folks, the way they operate is very different compared to us. It's more of silos. Analog is more of silos, and I think I thank Sanjay for this effort. Yeah, we should have more and more, conversations flowing so that we have ideas, and we might not be right, right, wrong to name, we might not be there as yet, which is why collaborations are the way to go. So thank you, Sanjay. Second is methodology first. Yeah, I'm challenging myself every time when I sit with a student debugging a circuit or something. I tend to say, ye to triode mein na, to do this. But then I'm like, okay, step back, hold on a little bit, because that can intimidate them. So methodology first, to think methodology first. Third, and the most important thing, is something that I learned in one of the management classes, which is disrupt yourself if you think you are good at something before someone who is not good at that thing tries to disrupt you. So my request to seasoned people, if they are attending the talk, is let's work together in disrupting ourselves and put method to analog circuit design. If you are in industry and your company is already doing that, we would love to host you and teach us more. And I would say code it up. Code it up is a very important thing, because I'm not sure about you, but I think traditionally there's this, how do I say, there's this less overlap between Venn diagram mein overlap itna kam hai from coding and analog. But I think if we can bring more and more methodology driven coding and not just automation like ghuma diya sab sweep kar diya type of coding, then it can do wonders for our field and have bright people come, and talent will be easier to find. This is it from my side. I tried to struggle between audience, academia, industry, and all. So thank you. And if you have more questions, if you want deep dive into any topic, I'm here. Yeah. That's it.
Thank you very much, Sakshi. Really, really insightful talk on GMID methodology. Quite interesting.
Thank you.
Yeah, so we are over time, but maybe I think we can take a couple of questions.
Sure.
Yeah, when we are waiting for others to come up, let me break the ice. Thank you for this wonderful talk, Dr. Arora. Tapas from Microsoft.
Hi, Tapas.
Hi. When do you think we are going to have AHDL, analog hardware description language? I believe things are coming in.
Yeah. Yeah, I honestly, I don't know when. It's hard to predict, but I know, as you said, the work is going on. I personally am not working on it, but super excited. I am following it, but I think sooner than later, because AHDL plus RL, I somehow feel that there is a good overlap and it should come soon. But Tapas, I don't have an answer of when. Do you have any thoughts on that?
No, not really. I mean, there are trials that went in,
Yes,
like
yes,
Berkeley Design Automation,
yes,
and there are a
yeah,
couple of other companies, and
yeah,
almost
yeah,
all
yeah,
spice CAD
yes,
vendors
yeah,
um, provide optimization
yes,
methodologies in it. Yes.
yeah,
The corollary to the question, how complex would that be in today's technology? Because
yeah,
you design the first pass, no problem,
yeah,
but after that, you waste mostly 70% of your design time on aging, on over voltage protection, etc. So do
yeah.
you think this rather Python enabled analog designers will be able to handle that and make it faster?
Yeah, that's an excellent question, Tapas. I think I think it's a multifold and a multi-directional problem, which the way the presentation that I had today, uh, I think analog is a long tail kind of a time with respect to taping out, and most of our time, as you said, is going into it goes into aging. Dekho circuit to design ho gaya, and the the paraphernalia takes a lot of time. But to me, the important thing, I could be wrong here, Tapas. I think her problem may what we need to break it down into like an RSS of these problems, and every problem has to be attacked via isolation में automation slash learning. I think machine learning बहुत underestimate किया है. The more I'm working with this professor, the more I think it is very powerful, and we can split it into problems. कि okay, Monte Carlo है, तो Monte Carlo के लिए there is uh, how do we attack machine learning say Monte Carlo? Is it RL? Is it neural networks? It is machine learning या Berkeley design automation ने जो काम किया. So every problem ka if we attack is like, which means it makes a humongous problem for researchers and for industry. But for you, I think it should be easier to pair each problem with attack एक one on one mapping बोलते हैं ना एक एक को कैसे isolated problems की तरह देखे. I wish I had better answers, but my gut feeling is हर को map करेंगे isolated problems में और हर किसी को automation slash learning के through attack करें. But yeah, I'm willing to brainstorm more on that, Tapas. Yeah.
Okay, thank you. I'll let others ask the question for the rest of the time.
Tapas, were you, sorry, I'll get it, but were you in ST?
Yeah. I spent major part of my life in SD.
Oh, so we would have crossed paths. I'm, yeah,
Perfect. Yeah, your name sounds very familiar to me. Yes.
Okay. Thank you. Thank you for asking.
Hello, Professor. Can you hear me?
Yes, I do hear you.
My name is Abhishek, and my question is in the context of this meeting. And
sorry, I missed.
Can you still hear me?
Yes, I hear you. My question?
Yeah, my question is related to probably the next part of your presentation, in which what happens is that when you are done with the sizing, then the problem changes from sizing the frets to compensate it. And I have found that two-stage LDO is probably good for the students and for teaching, but in the industry, especially if you are designing your lower nodes, you end up doing three-stage LDO, then Miller compensation, nested Miller compensation, and stuff like that comes into the picture. They rather take much longer time to fix things rather than sizing. So have you also focused in, automating those things because they are very interesting and complicated at the same time?
Yes, Abhishek, yes. As I was talking, I'll take lead from Tapan and I'll go to you. What we have done is I've split the problem into different students having different. So one of our students, one group is working on three-stage LDO. So we are attacking it from all sides because see, I have methodology for one. That doesn't solve the purpose at all. Say I'll tell you, oh, I have methodology for Miller compensated LDO. How does it make sense? You are designing hazard kind of LDOs. So one LDO will not solve your purpose, which means for any block, say I take OTA, I have N OTAs and N methodologies. that's when the machine starts to learn. So from my perspective, I am in a very nascent stage of thinking how RL or reinforcement learning can solve this problem, because of which I couldn't have just a one kind of a topology. So we have attacked it like crazy. So multiple topologies, multiple topologies, each topology tied to a methodology, so that we can train. You see where I'm coming from? So yes, it is hard, but yeah, so we are putting resources as much as we have on all of them. Hard, yes, I agree with you.
Understand. Thank you.
Yeah, yeah, and again, if you are willing to help, please, more than happy to have.
Hello, Dr. Sakshi. Can you hear
Hi.
me?
Yes, I do hear you.
Actually, I'm not sure it's exactly a question, but it's more like a thought. There are several designs that are realizable on schematic level, but when you actually go out to make the layouts, they tend to be not as successful because there are constraints for area and then cost, etc. So
Yeah.
there's a lot of back and forth one has to do to make sure
Yeah.
that these designs are also realizable on layouts. And
Yeah.
when this comes to like simulations, so when you do like variation analysis, reliability analysis, then you also realize there's also limitations over there.
Yeah.
So a system that is able to map a design
Yeah.
that passes on all these constraints,
Yeah.
would you think like that would be too heavy to be very practical in a design that is maybe used in industry?
I wish I had an answer, a clear answer for that. But I think I agree with you. Back and forth between layout and schematic, which means we were also thinking of post layout technology plots. But I think at some point it becomes a problem of diminishing returns. How much resources you put on the problems to fine tune to the last whatever percentage. But I think, as I said, I think when I was answering to Tapan, this is what I meant. Every stage को standalone we'll treat, and back and forth, I think it's valid. It will anyways happen if you are doing any other way of designing. This is only expediting your process vis-a-vis first pass at circuit design, not first pass taking you all the way. This is elevating that problem, but this back and forth, I think will still happen. I don't think it's cutting down that part of it, but maybe one problem at a time.
Yeah, sure. I mean, thank you for that. And I have another question which could be a bit beyond this. I read your bio and it said like you're also involved in hardware for health. So where do like Python for analog design, that is automation for analog design, and they cross? Like, where did you meet these two?
That we should talk maybe separately, but that's not analog IC design. I'm also working on systems. We are working on breath rate sensor, also working on circadian lighting for mental health. So that's a passion project for me. But that is orthogonal to, they have not met as yet. I don't know if they'll meet in the future. As yet, no overlap.
Okay, I
Okay,
think in
thank you
the
so much.
interest of time, we really have to close this. And once again, thank you, Dr. Sakshi.
Thank you,
Really
Sanjay.
appreciate for your time and the preparation that you have carried to conduct this session. And it was really insightful. And I hope interested people will get back to you.
Please do, please do. We hold
Thank
our
you very
ADEC talk
much.
series, so you're more than welcome to come talk to our students and have a look at the research, give feedback, and collaborate.
Yeah. Thank you so much. Bye
Thank you.
bye.
Thank you, Sanjay. Bye.